Hey everyone. I will be speaking in English, okay? So, Bayesian A/B testing with Python. A couple of months ago, Bayesian A/B testing and just in general, Bayesian methods compared to classical hypothesis, statistical hypothesis testing was kind of a hot topic, if you can call it hot. On the Hacker News, you could see the articles about Bayesian A/B testing, Bayesian methods, like a couple of them, 4 or 5. And at that time, I was an intern at a startup, and we were doing kind of research, and we were doing A/B testing. So we thought, oh hey, we should do it Bayesian way. It's so cool, it's so hot. I know it doesn't sound hot to most people, but we're not normal people. I won't be telling how do you implement A/B testing in your Django applications, because I don't know Django. I will be talking about theory behind it, about mathematics. So it's so many of you. Do you know that it's going to be a lot of mathematics? Okay. So I'll be talking about mathematics behind it. I will compare the classical statistical hypothesis testing approach, the Bayesian approach, and yeah, the difference between them, and maybe you make some conclusions. Sorry for that. So what is A/B testing? It's a kind of behavioral research study. The theory behind A/B testing, a lot of it comes from clinical trials. No, because it's kind of similar. You have control group, treatment group. You observe changes of behavior of your subjects. So for web development, it's kind of similar. So you have some variations of a web page, a couple of them, maybe 2 of them, maybe more. And you want to assess the performance of each variation. And you can do it using different metrics. For example, how much time does user spend on this variation of the web page? How many clicks does the user make? How many profit do you gain from the variation? Maybe it's an option. So, and you use statistical methods to assess the performance of this variation. So first, this is kind of a completely different approach from personalization. A/B testing is not personalization, it's like generalization. So for personalization, you want to fit to every user, and with A/B testing, you want to fit to everyone at the same time. For personalization, to every user it's separately, and for A/B testing, you find an approach that works for everyone. So they're quite orthogonal. So we'll take an example from web development. It's very simple, but it's quite practical. So say you have 2 variations of a web page. One has a red button, red sign up button, and another has a blue sign up button. And you want to know which variation will produce more clicks on the sign up button. I will call that sign-up rate, but it's not really sign-up rate, it's click-through rate, but it's my mistake. So let's just remember sign-up rate in this presentation will mean how many times will user click on each button. Okay, so, and you want to show randomly, show your users these variations. You may do it in a complicated way using multi-armed bandits, or you can just randomly show it. It doesn't really matter for now. So how do you deal with it usually? Yes, mass is coming. With statistical hypothesis testing, how does the model look like? First, how does data look like? For this example, let's just assume the data is a stream of binary data, I mean 0 and 1s. And we say we receive 0 and 1 for variation A, if user visited the page A and didn't click the sign up button, and we say that we receive 1 if the user visited page A and clicked the sign up button. Okay, so we have two streams of 0 and 1s for each variation. We have two of them. One important thing, a very important thing, that in this model, in frequentist model, statistical hypothesis testing model, we fixed the thing called population. So we assume there's an abstract thing called population. It's just a lot of zeros and ones, and it's fixed. And we assume it exists somewhere in our minds. And when the user clicks the buttons or visits the page, he randomly picks a 0 or 1 from this population. So in this model, the data, every piece of data is a random variable. Actually, it doesn't make much sense to me that the data is random. Because, you know, we have the data, it's fixed, we see it. Why should it be random? But in this model, the data are random variables. We assume that user picks them from the population independently. Every user is independent from other user. And in this model, it appears that the distribution of each random variable is the same. And it's the same as the distribution of the whole population. So for our case, it's Bernoulli. You can think of anything other for 0 and 1s. So we fix some sign-up rates. We call them PA and PB. So it may be, for example, 5% for variation A and 7% for variation B. And what we want to do is we want to learn these true sign-up rates using A/B testing. We can never learn them, right? Because it's just a very simplified model. But we want to. So once again, the important thing that we fix these parameters. We assume they are fixed but unknown. Okay? So usually you approach this with t-tests, and usually A/B testing calculators that you can find on the internet use t-test. So for that, you have a hypothesis that sign-up rates of variation A, variation B are equal, and you compute the t-statistic. So since we have our data random, the t-statistic should approach, the distribution of t-statistic should approach normal distribution as the number of data grows, or it should be t-distributed for smaller data. Because you see this x with a bar are sample averages. And the sample averages, since every x is a random variable, and the sample average is also a random variable. Because sample average is a sum of all data divided by number of them, okay? So it's random. And it should approach normal distribution. So what do we do is compute this statistic, this actual realization of this statistic. It's going to be one number. And we look where is it located on this distribution. And if it's located somewhere here, and maybe the hypothesis can be correct, it's likely to be correct, then maybe sign-up rates are equal. But if it's far away, this way or that way, then we are pretty sure that the hypothesis is not true, is not correct. And if it's this way, then we are pretty sure that variation A produces less sign-ups than variation B. And if it's that way, then we're pretty sure that variation A produces more sign-ups than variation B. So this is how it works. This number is for alpha 95%. Okay, so what do we have? First, we rely on large numbers. We rely on the central limit theorem and law of large numbers. That's one thing. Also, you always have to remember about two types of errors, type 1 and type 2. Type 1 is controlled by this alpha, which we, for example, set to 95. And type 2 is called power of the test. It depends on the number of data, and you need more data to obtain more data to have less error of type 2. Okay, and one important thing. So the problem with this approach is kind of philosophical, mostly philosophical. So what do we do here is we reason based on the likelihood of the data based on some hypothesis. Okay, so if you think about it, the vice versa would make more sense. We would like to reason based on likelihood of parameters, based on data. The data is fixed, okay, and the parameters, we don't know them. We don't know them, and we want to find the probability of parameters, the distribution of parameters. Obviously, in this model, this doesn't make sense because the parameters are fixed. They're just some numbers that we assume to be fixed, but we don't know them. And that's where Bayesian approach comes, with changing the definition of probability. Also, I have other philosophical problems, like this interpretation of confidence interval. It's really stupid. Like 95% confidence interval means that if you sample a lot of data from the same source, then in 95% of events, the parameters will be in this confidence interval. It really is not intuitive. So what do we do with Bayesian approach? We say that probability is our quantification of quantification of our knowledge about something. So now we say that parameters are not fixed, they are random variables, and by random we mean we don't know them. And we quantify our knowledge about them using probability, using this number from 0 to 1. Okay? So now we have everything vice versa. The data are fixed, because it makes sense, okay? Data really are fixed, we see them. They're not random, all right? So the data are fixed, and the parameters are random. So we need to set the likelihood, which for our case of click-through rate is binomial. And we need to set the prior distributions, which quantify our prior knowledge on parameters. So ideally, since we know nothing from the start about the parameters, it could be like a flat line, something. So every value from 0 to 1 is equally likely. And then when we have more data, when we obtain data, this distribution changes, and it reflects our change of belief in the values of parameters. So to conduct the test, we want to find these probabilities. The probabilities that variation A sign-up rate is better than variation B's, and vice versa. And also lifts, which are distributions now, since these are random variables. So previously I have picked the beta prior on the parameters, because if you have a binomial likelihood and you pick beta prior, then when you write the Bayes theorem, yes, this is Bayes theorem, that's why Bayesian, then everything cancels out beautifully, and in the end, it's again beta. So it's kind of this online updating algorithm now, because this posterior distribution is beta distributed. And then, so you obtain data, calculate the posterior distribution, it's beta with some parameters. And then when you obtain more data, you can just repeat this procedure by putting previous posterior in the place of prior. So you see, it's kind of different. It's an online algorithm that you can update with more data. And what you have to store, you only have to store this state, these parameters of prior. Okay. Also now, with this approach, this confidence interval that I was talking about is called credible interval, and it makes a little bit more sense now, because it actually is an interval, like 95% credible interval is an interval where the parameter lies with 95% probability. It's really clear, it's really intuitive. And also, you can just pick any prior and any posterior distributions. It's really cool. You don't have to recalculate the mass. You can use just some special packages like PyMC or even SciPy to do this kind of test with any distributions. And you don't have to recalculate the statistical hypothesis testing. So you can use Monte Carlo methods to compute it. And since I have have chosen the conjugate prior, the beta, it cancels out beautifully. You don't have to use Monte Carlo method here. Okay, so what do we have now? We have similar assumptions, the same independent Bernoulli trials, so the setting didn't change much. Philosophically, it's a little bit better. So we don't rely on large numbers in theory now. Of course, the size of the data still affects our errors, but we don't rely it in theory. The credible interval can be interpreted intuitively. So it's an interval where the parameter lies with some probability, because the parameter is a random variable, so we can say that. But the most important thing is that we actually changed the definition of probability. We changed the model completely, but it appears that this is just a generalization of the frequentist statistical hypothesis testing method. There's an error. No one will notice. Okay. Previously we were finding the likelihood of data conditioned on hypothesis, and what we do now is we integrate over all of the hypotheses. It's kind of generalization. And actually, we obtain the distribution, and we can do much more reasoning with this distribution than with just what do we have? The statistic value. And also the program, the software architecture is different now. So we have online algorithm. So we obtain a piece of data, we update our state with a piece of data, and then we analyze. And we can shut the test, stop the test, or we can continue obtaining data. Okay, so how can you do it with Python? So here, for example, I have some example data. So we have two variations, A and B. We have 42 views. Yeah, the number of views doesn't have to be equal, actually. We have 42 views for one, 85 views for another, and this is the number of signups. You calculate the posteriors, beta distribution, using that formula that I showed you. And with these posteriors, you can print interesting values, like expected value of a parameter. Like for this case, expected value of parameter for A is 5%, for B is 13%. You can print credible intervals. It's also easy. And yeah, you can do Monte Carlo simulations to compute more complicated things. Like, well, the most important, the probability that one variation is greater than another. We can use this kind of Monte Carlo approach to compute it. So for this case, the probability that variation B is better than variation A is 92%, 93%. So I made a small library for this. We're doing exactly this. It's called trials. It looks like this. You instantiate a experiment object with some type, Bernoulli for this case. You update it with data, and you can obtain these values that I was talking about previously. So the dominance is the probability that sign-up rates for one variation is better than another variation. Credible intervals for each variation. Expected lift. What is lift? Lift is how much one variation is better than another. So you have a lot of them in this library. You have expected lift, credible interval, empirical lift, dominance, expected posterior credible interval. That's it. I really would like to hear some suggestions and corrections, because I probably have some errors here, maybe. So, okay, and now I want to show how it looks, so you can imagine a little bit. It's not going to be fuzzy-looking plots. So how does it look like in the beginning? So variation A, variation B. On the x-axis, you see the value of parameter, and here you see the kind of probability. It's not normalized, whatever. So you see that in the beginning, every value is equally likely because we don't know anything about the parameters. Okay. By default, actually, it's not this way. By default, it has other parameters, 0.5, 0.5. It looks like this. So by default, 1 and 0 are more likely than anything in between. I don't really remember why did I do that, but I'm pretty sure there was some reason. It's something like Jeffrey's prior. I forgot to check it. Sorry. Okay, so say we update it. Say we have for every variation we have logged 100 views, and we have observed that of these 100 views, for variation A, 50 people clicked on the sign up button, and 50 people didn't. Okay, and for variation B, 90 people of 100 clicked the sign up button, and 10 didn't. So now what do we have? We have different posteriors. They reflect our current knowledge of the parameters. So see, since variation B is obviously better, it's green, right? So this plot is the expected value is higher than expected value of this one, and you can see that. Let's see what happens if it appears that later on variation A performs a little bit worse. So we have 20 signups for A and 50 signups for B now. Okay, since it wasn't really bad change, the variation B is lower now. So it was 0.9. Now it's 0.7. And now see what happens if variation A becomes really dominant. It approaches, right? It reflects our knowledge about that. And now the last time, the variation B produces 0 signups, and variation A produces half of the signups. So it become bigger. A big problem is when do we stop the test? And for this, we can sample the thing called lift that I've talked about. It's simulated, so we don't know the real distribution. We don't know what distribution it is. So I've simulated with sampling. And what is it? BA. Okay, so this is how much percent. Okay, it's not percent. It's on scale from 0 to 1. So this plot means that it's most likely, based on the current data, based on the current knowledge, that variation B is 15%. I think it's 15. Is 15% worse than variation A. So one option to stop the test. So that's a problem. I don't really know how to when to stop the test. I've asked the author of the book, Bayesian Methods for Hackers, and he proposed this method. So you look at the lift, and you stop the test when the peak is very high. So you can measure the kurtosis, the sample kurtosis of this distribution, and if it's very high and very thin, then you can stop. But it becomes hard with a lot of variations. So for now, you can just run the test, and stop wherever you want. Okay. So that's pretty much it. Thank you. And I'm ready to hear criticism and questions.
do you remember all the updates and samples from updates? Because you here got a number of samples. Are they kept in this class?
Well,
all the history of updates, or are they just recalculating everything?
No, only the current state. Only two numbers, parameters of the beta distribution for this case. This number of samples is just some big number. It's completely different. It's just kind of a way to generate this leaf distribution.
Okay.
It's different. So I have a book for you. It's Python N HDF5. Okay. And I have another book. So, one more question at least.
Okay. I have several questions. So,
okay.
If anybody feels that he has better ones, please stop me. So the first one was, do you have to have the same number of samples in every group you are comparing?
No.
Okay.
No.
First one.
But that is reflected in this leaf distribution. So probably if there's a big disparity in the number of samples, this distribution will be not enough to stop the test. The peak will be not that big enough to stop the test. Okay. But it's not necessary.
Okay. Does it use some assumptions about the distributions of the data, like the t-test? It required a normal distribution. Does this require some distribution?
Well, we assume the binomial likelihood.
Mm-hmm.
So we assume a lot of things here. We assume that data are independent. The experiments are independent, and we assume that before the start of the test, we don't know anything about the data. And we assume that, this binomial likelihood.
And the last one, was the difference in number of samples you are you need to acquire the statistical significance between this approach and the t-test approach?
So that's a problem I was talking about in the last sentences. I'm not sure when do you need to stop, because you don't have type 2 error now. So for statistical hypothesis testing, you had type 2 error, and it depends on the size of the data. But now you have you have marginalized this hypothesis. You have integrated over all hypotheses, so you don't have this concept of type 2 error. But so this is one approach. You can look at this leaf distribution, and when the number grows big, it will become higher and higher. But I don't know the exact formula, how much high it has to be, depending on the number of data.
And in general, you need more users or more samples or less?
More users? No, yeah, more data. In general, you need more data.
Okay. Thank you.
With standard A/B testing, not in Python specifically, there is a problem and the possibility to introducing a bias if you wait for the number of samples that shows some significance in the data. So you do A/B testing, and you just wait to see when the one option becomes better from the other. Mm-hmm. And I've heard and I've read some math that says that if you wait for the significance, you are actually introducing bias. And if you don't know when to stop, you should just fix the number of samples that you are going to collect, and don't look at the data during the collection, and just see at the end what the data shows, because it can show that there is no difference or there is no significant difference. Is this the problem with this method, or does this remove this problem?
So the bias introduced by too many data? Yes.
The bias introduced by stopping the experiment when you see some initial significant difference between the samples.
So the thing you're talking about is that usually with statistical hypothesis testing, people tend to stop the test when they see that significance is lower than alpha, somewhat lower. So we fix alpha, or it should be 5%, right? but they don't look at the type 2 error. So this type 2 error depends on the size of the data. And for every percentage of error, there's a certain amount of data that you have to obtain before stopping the test. So that's a problem what you're talking about. Yes, it is a problem because I don't really know when to stop the test. For hypothesis testing, you know when to stop the test. Yes, and it's calculated from the power, from the statistical power. Yes. The book. Oh, I'm sorry.
So you said that we're running a lot of assumptions here, and how does it compare to, maybe not compare, what influence has it on our experiments results? Like, do we need to specify the problem much more than we did already to get realistic results?
Okay, so both approaches have kind of not realistic assumptions. So in both cases you assume independence, right? It's never independent. So when you so when you collect the data, for example, for web page visits, it's never independent because I don't know. There are people from China that get up late at night and they like red button, and then China sleeps, and then US goes to your web page, and they like more blue button. So, for example, in this case, the data are not independent because of the geographical location. This is the same. This has the same assumptions on independence, so it also has this problem. To deal with it, well, one thing you can do is to run separate A/B tests for different groups of users, for example. But if you think about it, it's going to personalization. So the more you want to split the A/B testing, the more it is of something of like personalization. Okay.
So again, about assumptions.
Yes.
How do you actually choose the distribution of the confidence?
That's the thing I forgot to stress. So I've mentioned that with this approach, you can pick any distribution you want, right? And you don't have to recalculate the hypothesis statistics and stuff like that. So how do you choose? For example, for the number of clicks, it's binomial. If you want to measure the time spent on the page, okay, so it may be log normal, for example. Like, it looks something like this. If you want to measure number of clicks, it's going to be Poisson, okay, so it also looks something like this.
Sure, but how do you know that?
Well, I don't know, just experiment.
Okay, so how would you set up this experiment to know the distribution of the variable that you are going to measure?
Well, you can just collect the data, okay, and see if it fits the distribution.
I don't see, that's why I am asking question on different level. Can you tell more about your tool that you use to visualize the data here?
It's IPython notebook. So the tool that is used to visualize it's matplotlib. It's a Python library for plots. And I'm using this style, not style, but I'm using this library called Seaborn, which makes the matplotlib plots look nicer. So that's it, yeah. It's Python 3, NumPy included, SciPy included, and matplotlib is included by default when you run the IPython notebook in this mode. So, yeah,
Thank you.